Okay, so hello everybody. So here's a summary of what we did last time. I want to finish this. The job for today is to finish the discussion of that. And then finally, go to algebra, because you see the title of this class is algebraic knot theory, so there should be some algebra. There will be a lot of algebra. Anyway, so let me remind you, we defined ribbon knots and talked a little bit about ribbon and slice, but we actually didn't yet finish the discussion. So ribbon knots means a knot which bounds an immersed disk in which the allowed singularities are z's, but the disallowed are z's. Okay? And then we also proved that every knot is the boundary of an embedded surface with boundary, sigma g1 for some g. And then we defined the minimal, the genus of a knot to be the minimum of all such surfaces, the minimum of the genus of all such surfaces. And then we have the statement that every knot of genus G is the boundary of an embedded, well, that's by definition, it's the boundary of an embedded sigma G1, which looks like that. But it also looks like this. It's the thickening of a G-camel caravan of two hump camels. Okay? And I want to say, I want to state one further statement, which is not very difficult, but worth stating. You'll see why. Okay? So let tau sub g be the following map, or be a map from the knottings. So as I write the theorem, I'm introducing a notation. Okay? So the knottings of a picture like this. So what I mean by a picture like this, so actually I wrote it as if it's already knotted. In a sense it's wrong. I should have written it this way. Okay, this is the skeleton of a knot. So the skeleton, or of a tangle, or of a link. So maybe on the side I should say what I mean by the skeleton. So the skeleton is basically the parameter space and information that comes with the parameter space that has nothing to do with the embedding. So the skeleton of a knot, of an ordinary knot, is a circle. But it's an abstract circle, it's not an embedded circle. The skeleton of a link is a pair of circles, and so on. The skeleton of a tangle is just a bunch of lines. But you see, when possible, when necessary, when appropriate, I retain the ordering of the endpoints. So here the ordering is 1, 2, 3, 4, and here it's also 1, 2, 3, 4. But you know, on the other hand, if I wanted to look at knottings of this skeleton, then knottings of this skeleton will be any knot that is, or any tangle that's made of two components and whose components are connected, have the same connectivity as this, whose endpoints have the same connectivity as that. So this would be an example, that would be an example, but also, I don't know, sorry, I'm just making up something. Also that, okay? Sorry, this isn't a particularly good drawing, okay? So basically I want notings of this skeleton, okay? So there is a map tau sub g from notings of this skeleton to notings of the circle. And the map is defined by, so what you do is, so suppose you have a noting of that skeleton. Being unimaginative, I chose a stupid one. But this could be more complicated, right? This could go, well, like that. Okay, so any noting of that skeleton, what you do is you double each strand, so you double each of the strands, and then you, well, strictly speaking, by the way, I should have specified orientations. So now everything is oriented to the right. Then you reverse the orientation of the inner strand in every pair. So you, or if you wish, you double, but with reversing the orientation of one of the sides. And then you connect as follows. So you connect this to this, this to this, this to this, this to this. Basically, you connect skipping. You connect the pair and then you skip one. Connect and skip. And finally, you connect the last to the first. Okay? So this is, in other words, the order is double, reverse 1/2 of the strands, and connect in a certain, according to a certain pattern. Anyway, sorry, so far it's a definition, not a theorem. And now comes the theorem part of the theorem. So the collection of all nodes that was studied here, the collection of all nodes whose genus is less than G, is equal to the image of tau G. Proof, well, we've more or less proven it. I just wanted to state it. So let's see. One inclusion is what we've done, right? So clearly, if you have something in the image of this construction, then it's the boundary of an embedded thickening of a caravan of 2 hump camels, and therefore it's the boundary of a sigma G1, therefore it's a knot of genus at most G. So this inclusion is obvious, or done, essentially, and it remains to show this inclusion. So I can do it more abstractly and a bit less abstractly. So let's do it slightly more abstractly first. So suppose you have a knot of genus G. It's a knot of genus G, therefore it's the boundary of an embedded thing like this. Right? But this thing is homomorphic to this thickening. So your knot is known to be, so if K belongs to the left, if, I don't know, K0 belongs to the left here, then it's known that K0 is an embedded, or is the boundary, is the boundary of an embedded picture like this. Sorry, I'll do it with only with g equals 2, the picture, because it takes less time to write. So it's the boundary of an embedding like this. Okay? An embedding of a surface like this. But you see, take this surface and mark in it on red, in red, its core. So mark on it a thing like this. And now look at the bottom line of the core. The bottom line of the core is just a contractible line, right? The embedding of the picture, right? I'm not drawing the embedded picture, I'm drawing the parameter. In the embedding, this line could have been knotted, could have been curved, could have been crazily knotted, okay? But on the other hand, you cannot knot a line in R3, a smooth line in R3. Every smooth line is unknotable. Okay, I think I haven't shown that, but it's kind of, well, it's at least known to anybody with experience with ropes. But basically you can shrink the line along itself until it's a small interval, and then that interval is nearly straight. Okay, so by applying some homomorphism of R3, I could assume, or by doing some motion, I could assume that this line is in fact straight. Okay? So this line and likewise a small neighborhood of it. So I could assume that this is actually genuinely straight, or flat and straight. And then the complement, namely the red stuff, the remaining red stuff, is a tangle. And it's a tangle whose skeleton is precisely the skeleton I wanted. And now, right, so now red is a tangle. So red is a tangle. And white is exactly that thickening of that tangle, or that doubling operation applied to blah, 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 okay? Doubling, reversal, connection applied to that tangle. So strictly speaking, you know, this is an embedded surface. It doesn't have to look like this. So, in other words, like the surface could have had ears, flaps. Think elephant ears, okay? But it doesn't matter. You can contract it to the core, and then it's just you can contract it towards the core, and then in R3, and then it's just a pair of, and then the boundary is just a pair of lines adjacent to the core, on opposite sides with opposite orientations, which is exactly what tau g would give you. I think I think this is enough. I could say more, but well, I don't think I want to say more. This is enough. I just want to move on. So that's all. Oh, wait. So what's the moral? The moral is, so you see, I already gave you reasons to care about tangles. So the reason was computational speed, okay? But now I've given you another reason to care about tangles. So if you understand tangles, so the moral is, we want to understand. So understand in the context of this class will mean find homomorphisms from this topological collection to algebraic things. So we want to understand tangles, and I've already explained well, okay, we want to understand tangles, but we want to understand tangles meaning along with their planar algebra operations for computational reasons, but also along with doubling. So if you have one strand, you want to know how to double it. So if you had an invariant of tangles that somewhere had a strand there, you want to compute from it the invariant of the tangles that you will get by doubling that strand. And reversal. So if you have a strand, you want to be able to compute the invariant of the tangle that you will get by reversing this strand. All of this will become more formal later, but at the moment these are morals that I'm keeping for myself. Still a bit informal. Okay, that's all I had to say about genus G knots. So the chapter about genus G is done, and now I want to, or at least done for now, and now I want to say something about ribbon knots. So I want to state a similar theorem. So theorem, but for this theorem, I need two definitions, two maps. So so first of all, let me introduce the setup. So I want to talk about tangles whose skeleton looks like this. So in general, some number n some number n of strands. Well, basically, the skeleton is like that. So some number n of vertical strands, some number n and an equal number of cups like this. Okay? So given a knotting of this skeleton, so I mean, ignore the box. The box is just sort of a frame. I mean, the skeleton is just the vertical lines and the cups. Okay? So given a knotting of this skeleton, there are two things I could do to it. I could apply the operation delta. So the operation delta deletes all the cups. Sorry, no. Deletes all the vertical lines. So you're only getting the cups, and you get n of them. And that's just a smaller tangle. So it's an operation from the knottings of this skeleton to the knottings of that skeleton. And there is a second operation, which I will call tau, and forgive me for the reuse of the same letter, but we're in a different context. And tau is defined as follows. So if I have a tangling of this, so a tangling of this happens within some box. So everything that I'm going to do now happens either happens in a neighborhood of a strand or outside of the box. So first of all, you double all of the vertical lines, and then you make connections as follows. So you connect this to this and this to that, this to this and this to that, this to this and this to that, and on the other side you connect this to this, this to this, and this to that. So, I mean, the picture, in this picture, everything outside of the rectangle I've just drawn is exactly how I've drawn it. But everything inside the rectangle I've just drawn could be noted. So, in other words, if the original tangle was called T, the map delta copies T's but delete the verticals, and the map tau copies T's, doubles the verticals, and make connections outside as explained. Okay? By the way, the map tau is a composition of the maps we already have, namely doubling and reversals. I should have said that, well, if these were oriented up, then here some would have to be oriented up and some would have to be oriented down to make it orientable. So the map tau is a composition of doubling operations and reversal operations and the planar algebra operations. The planar algebra operations were used to basically to stick a fixed tangle at the bottom and a fixed tangle at the top. Well, okay, so far it's definitions, but not yet a theorem. But maybe one more thing about the definition. Here I use the new operation, namely strand deletions. Okay, so yet another operation of interest among tangles is strand deletions. If you have a strand, you have the operations that deletes it and gives you a smaller tangle. Anyway, what's the theorem? The theorem is that the set of all ribonauts is the collection of all it's the image under tau of the things whose image under delta is trivial. So it's the collection of all tau of t such that delta of t is equal to the untangle. What's the untangle? So the untangle is with this skeleton, is exactly what you would expect. So it's, it's this picture taken literally, not noted. Or said differently, it's this picture with the further assumption that each of these little cups bounds an embedded disk whose, or embedded half disk whose equator lies on the boundary of that chunk of space. Okay? Good. Well, so again, it's a theorem, so it should have a proof. And again, there are two inclusions to consider. Yeah?
So is it as a setter? I don't quite get it. So we have the untangles and on this side, and we have the ribbon on this side. So how do I relate the two?
Sorry? So
again,
again,
I think I get it. The
okay.
set, okay.
Okay.
Thanks.
Maybe before proving, what's the significance of that? The significance is that the set of ribbon knots has a description completely in terms of tangles. So if we're able to find a homomorphism from the world of tangles into some world in algebra, then we might get information about ribbon knots. Okay, that's the significance. Okay, so again, we need to prove two inclusions. So let's do the easy one first. So suppose you are in this set. Okay? In other words, suppose you have a T whose delta is the untangle and whose kappa and whose tau is our knot. Okay? Suppose T is in the knottings of this shape with delta T equal to the unknot. I need to show to you that tau of T is a ribbon knot. But let me draw T slightly more in a slightly more interesting way. What do I know? Okay, here is the skeleton of T. But what I know about T is that the caps part, if you ignore the vertical lines, is trivial. If you delete the vertical lines, the caps part is a trivial thing. So you can deform it to be a trivial thing, and all those strands deform along. Okay, so without loss of generality, the cap things are as they look in the picture. However, the vertical lines, right, while you deform the cap things to look exactly like that, the vertical lines might get knotted with each other, or they might have been knotted with each other at the start. But they may also get knotted with the cap parts. Okay, so basically they may look like this. Well, and it could be more complicated. So this one could go through this cap, then out and through that cap, and then that here. Okay, but it could be more. That's the schematic of the picture. Okay. Now let's do let's compute tau of this. So how do you compute tau? You double the, you know what, sorry. Even before computing tau, let me do a, no, sorry. Let's compute tau first. So what does tau look like? Well, you know what? Yeah, okay. You know what? Let me draw it this way. Tau, sorry, I'll explain my picture in a minute. So tau colors each of the vertical strands in orange, where orange means, so a line in orange means just a pair of lines like that. Sorry, that's the easier way to draw a pair of lines, okay? So, tau paints all of these in orange. Except at the ends, I wanted to remember that that an orange line is really a pair of lines, so I drew it as a vertex. Okay, and then tau makes connections like this. But now you automatically get a disk. So it's actually easier to see the disk here. The disk is this disk along with a piece of a disk here, a piece of a disk here, a piece of a disk here, and these n+1 disks, so n disks at the top and one at the bottom, are connected with bands. So really this looks like a single disk in the middle with n satellite disks. If you've ever been to the old terminal in Paris, the Charles de Gaulle Terminal 1, I think, then that's the structure. Anyway, it doesn't matter. And but that is homeomorphic to a disk. This is just a disk. A disk with n disks attached is just a disk. So we have a disk here too. This is like the hub, and out of the hub come n ribbons, they are orange, and then each ribbon expands to a satellite terminal, okay? So a satellite disk. Okay, so basically our picture bounds the blue disk. What singularities does this blue disk have? Well, the orange lines don't intersect each other, so the bands that they become also don't intersect each other. The hub at the bottom is outside of all the mess. So it's constant. It's just as it looks. The only intersections are where the orange ribbons, the orange bands, pass through the blue pieces of disk. But these intersections are precisely so. Each orange is really a pair of things, and these are ribbon intersections. End of story. QED. Okay. So, sorry, QED for one part. Now we need to do the other part. So, so let's look at the other inclusion. So the other inclusion, wait, which one did I do? This one. So now I need to do that. So suppose you have a ribbon knot. Suppose K is ribbon, and suppose it bounds a disk, so bounding a disk D that has only ribbon singularities, that has only ribbon singularities. So here is D, and I'm drawing it from the perspective of the parameter space. So this is D, this D then gets mapped into R3. But I'm drawing the domain. It has ribbon singularities. What do ribbon singularities look like? So a ribbon singularity is, well, it's a singularity. Every singular point has two pre-images. So this singular line has two lines as its pre-images. And one line goes from an internal point to an internal point, and one line goes from the boundary to the boundary. So every singularity is really a pair of lines, one like that and one like that. Okay? But these, sorry, what have I done? And one is internal. So one like that and one like that. And these are pairs, are paired. So maybe we should mark this one with 1 and this one with 1, and there could be more. So there could be another 2 here and 2 here, which is paired to it. But there could be more. And in fact, nobody says that they're straight, clean, elegant lines. So, you know, there could be line number 3, which is paired with line number 3 here. Okay? And then, and there could be number 4, which is paired with number 4, and so on. Okay? So that's the domain space picture of a ribbon knot. Now, so by an annoying multiple applications of the Jordan curve theorem, so and variants of the Jordan curve theorem. So you know, the Jordan curve theorem says that if you have a messy disk, it's actually homomorphic to a standard disk. Okay, sorry, a messy circle, then it's homomorphic to a standard circle, and its interior is homomorphic to the interior of the standard circle, and so on. But there is a similar relative theorem. So if you have a curve within a disk, then you can find a self-homomorphism of this disk, which will straighten this curve. So you can straighten this curve within this slice. And then you can straighten every piece within where it lives. Okay? So you can replace this picture with a picture in which all the lines are straight, or not straight, I mean topologically simple. No, geometrically simple. I forgot. So, okay, this is 2, this is 3, this is 1, this is 1, 2, 4, 3, and 4 is here. And the only reason I'm doing it is because it's easier to see it. Topologically, it makes no difference. It's the same. But it's just easier to see it this way. Yes?
Yeah, could you explain the pairing again? I don't get the picture from here.
So you see, these are singularities. And a singularity is where a pair of points in the disk gets mapped to the same point in R3. So when I label this with 2 and that with 2, it means that this interval in the image is equal to that interval.
Oh, I see.
So in other words, in a ribbon knot, you have multiple ribbon singularities. You'll just temporarily label them 1, 2, or 3. You know, you'll just temporarily give them names. And then if you're looking at singularity number 5, then all of its pre-images I'll label with 5. And then I'll know that line number 5 is matched with line number 5 with some other pair, other place. Okay, next. So what isn't marked as a singularity isn't a singularity. Okay? So what you can do is you can contract the knot or pull the knot along this line and also along this line. Of course, I could have just done it on one side, but I don't know, it's nicer to picture it this way. So I'll do it here and I'll do it this way for all the singularities that for all the singular lines that span from edge to edge. So I do it here, I do it here, I do it here, and I do it here. Sorry. So what does this picture looks like now? Okay, so first of all, the new disk, the new circle, which I'm now marking in blue, is equivalent to the previous one because you could contract, there is nothing singular happens here, so I could push this strand out to where it was before. So this is equivalent, the knot you get now is equivalent to the old one. And it's presented as the boundary, well, it's still the boundary of a disk, but now this disk can be seen as a union of disks. So it has sort of chambers, and these chambers are themselves disks. And in between these disks are connected with bands. Each of these pieces is a band. So, and furthermore, the disks are trivial, or they bound trivial, their boundaries are trivial pieces of knot, because there are no singularities within each of the, these, wait, what do I want to say? These disks, yeah, if you look at the boundary of each of these disks, so say the boundary of this disk, so I forgot to mark it. There is this the boundary of this disk. The boundaries of each of these disks, well, is trivial because, well, or even this bigger disk here, its boundary is trivial because I have just demonstrated it as a boundary of a disk. And that disk, well, you know, maybe I should have looked at this one. So this disk has a singularity, but the singularity is with some line number one. Line number one was, which one was this one? Was with line number one, and line number one is inside a band. The other side of line number one is inside a band. So just this disk in itself is non-singular, right? The singularities are always sort of an intersection of a disk piece with a band, with a band thing, and they don't So the disks in themselves are non-singular. So this picture is really a number of disks in R3. Maybe I'll draw them in blue. And in fact, the totality of these disks, if you just look at the link made out by as the boundaries of these disks, then it's a non-singular link, because each component bounds a disk, and and these disks are pairwise disjoint. Okay, but then you have bands. So each of these rectangles is a band, and it's a band that goes from a small interval on the boundary of one disk to a small interval on the boundary of another disk, and it may have a singularity in it. In fact, it will have a singularity in it. So these disks are connected with bands, but these bands like this band might connect from here to here, but on the way it might pass through the interior of some disk. Okay? And then this disk will be connected possibly to that one with another band. So our knot is now a thickening of a graph. How much time do I have? Barely. So our knot is now a thickening of a graph, which might be, which is a tree, because the overall thickening is a disk. So it's a thickening of a tree, and the tree is made out of blue circles and red lines. Each blue circle is really representing a disk, and the totality of the blue circles make the unlink. And the red lines represent bands, and the bands are not intersecting each other, but could be passing through those disks. Okay, so I've described the picture. But now, but this could be a complicated graph. So I don't know, this could have, it could be, a complicated tree. But you can always slide bands across each other. So you can take this band, slide it along this band until it connects to here. Now, whatever singularities this band might have crossed, this one will cross in a parallel manner. But that's still, these will still be ribbon singularities. These will still be singularities in which this new red line crosses through one of those blue disks. So by but every tree, whenever you have a tree, if you can slide the edges across each other, you can bring it to be a line. You can bring it to be a long, even better. You can slide all the edges to one of the vertices. So you can bring the tree to look like this. So a hub and spokes. Spokes. And again, the disks, in fact, the disks are the same disks that they were, so they haven't changed. So the disks are as they were, and the band, the ribbons, passively go through these disks. Also, you can empty one of those the hub. So basically, if you have any red line passing through this hub, you can slide it out using one of the spokes. So you may as well assume that this one is empty. But this is, okay, I'm out of time. But this is exactly the picture we had. This is exactly what the Tangle generated, produced. So I'm sorry, yeah, I'm sorry. I should have prepared the pictures better in advance, but so be it. Okay.